Hello, good afternoon, everyone. Thank you for joining us. We'll start in a couple of minutes. We'll just give it another minute for a few more people to join, and then we'll get started.
Mark, just to let you know you're on mute.
Thanks, Anya.
No.
Hello, everyone. Thank you for joining this Analog Devices and Mouser webinar, Solving Precision Measurement Design Challenges in Low Power Applications. My name is Mark Patrick. I'm Technical Marketing Manager for Mouser Electronics here in EMEA. We have around 20,000 analog devices parts in stock for quick delivery. And for those who don't know, Mouser is a global distributor of the newest semiconductors and electronic components from over 1,100 manufacturers. Throughout the webinar today, please ask any questions you may have on the presentation using the Q&A button below, and we'll answer as many as we can at the end of the presentation. If you have any technical questions around the webinar itself, such as audio or webinar functions, please use the chat function and someone from the Mouser team will help you as soon as we can. But without further ado, let me hand over to Anya McCarthy, Applications Engineer for the Precision BU at Analog Devices. Anya.
Thanks very much. And it's great to see that so many of you have joined us today for this webinar that focuses on solving precision measurement design challenges in low power applications. The webinar today will involve an overview of precision at Analog Devices. We will go through what we mean by precision low power signal chains, and will then discuss low power application examples and talk to some of the design challenges associated. We will then focus on what ADI has to offer to solve these challenges for customers. I will then show you where to find additional information. Precision at ADI spans across several technology franchise areas, from ADCs and DACs to amplifiers, switches and multiplexers, and also isolation technology. These are used in a multitude of different end applications across multiple end markets that include industrial, healthcare, and instrumentation, to mention a few. These applications depend on core technology to enable innovation from sensor to bits and back again, or in other words, ensuring accuracy, precision, and the highest quality of both measurement and drive signals within the end system design. If we take a look at these precision technology products on offer, there are thousands of products that fit into hundreds of end applications. So to make it even easier to navigate the breadth of precision technology available at Analog Devices, we have brought together precision signal chain solutions that are built on these core technology pillars. We will walk through some of these throughout the webinar today. These signal chain solutions are combined in a way to ensure that they solve customer problems in different end applications and markets. And we do this by providing an easy-to-use, more complete starting point for system designers. We want to make sure that it's easy for our customers to find what they need and evaluate for their end solution as quickly as possible. For this webinar, we will focus on applications where precision, power consumption are really critical. And for this, we will focus on precision low power signal chain solutions. So what do we mean by our precision low power signal chain? These signal chain solutions are a combination of our best-in-class low power technology. They are an accelerated starting point offering capabilities across multiple end applications and have been optimized for DC precision at extremely low levels of power consumption. The signal chains operate from supply voltages of 1.8 to 3.3 volts and offer performance from 16 to 24 bits. Size and channel count have been taken into consideration. But not only these, we have also brought together solutions that can be optimized even further to enhance longevity in the end application. These signal chain solutions offer an excellent starting point for low power designs. And through this technology, we can certainly offer differentiation, which enables efficient, autonomous, precise measurements, small solutions that are easy to scale, and enable extended operating lifetime through inherent power optimization techniques. So I guess we're enabling faster, precise insights where it matters in the end application. Within the low power signal chain platform, there are different solutions that are tuned and optimized to offer key benefits and trade-offs depending on the end application. We have solutions that are single-channel, multi-channel multiplexed, and also multi-channel fully integrated solutions. And each of these will be discussed a little bit in more detail as we go through the webinar. So when we look at the design challenges, there are certainly many that exist. Here I've highlighted a number of key challenges that system designers usually consider. Some are more important in their end application. For low power design, and really any design, there is always some trade-off that will need to be considered. This means that it's really important to strike the correct balance for your design. For today's webinar, we will focus on 3 example applications where low power is a key design requirement: field instruments, condition monitoring, and portable medical devices. For each of these example applications, we will discuss an applicable signal chain solution that is optimized with low power and precision as key factors. For each, we will highlight the value proposition of the signal chain and also discuss any tools available that enable optimization or even further tuning of the signal chain. We will then discuss some product spotlights, giving an overview and the benefits of each of the products. So let's start with field instruments. For field instruments, some example measurement modalities include temperature, pressure, and flow. These are just a few, but there are certainly many more. If we look at some of the design requirements associated with field instruments, size is really important, as it's the main constraint after power and precision. Reliability and precise measurements are really important for field instruments also, as decisions are made based on the reliability and accuracy of the measurements being made. Scalability is another key consideration. This enables the solution to be easily scaled from single to multi-channel solutions, and also potentially have the ability to connect to different sensor types very easily, leading to a solution that are easy to configure and have the features available to enhance low power operation and extended lifetime in the field. Taking temperature as a focus, this is a common modality for field instruments, but also for many applications beyond this space. If we focus on field instruments in particular, system designers face significant challenges in ensuring highly accurate measurements. From figuring out the right sensor for the end solution or being able to support multiple sensor types can be a regular design challenge. If we look at some of the requirements for these sensors, and for this example, we've called out 3 different types of temperature sensors here: thermocouples, RTDs, and thermistors. It's important for the end solution to easily excite and bias these types of sensors, thus ensuring that the signal from the sensors is at an optimal level so that key information is easily extracted. Some of these sensors require ratiometric measurement, others require really accurate biasing or a really stable reference voltage. In some cases, being able to scale from single to multi-channel is also really important. If we look at the environments where these end solutions are placed, they're often very harsh. So robustness in your measurement is certainly an important key factor. Thus, it's important to have solutions where the results are always accurate and reliable. These design challenges alone can lead to complex designs and add to very long design cycles. But if we look at the solutions that are available from analog devices, and we'll go through some of these in a short while, we're not just addressing the design challenges, but we also bring capability that really enhance the end design, from space saving to sensor measurement to autonomous measurement and diagnostics as examples. To address the requirements and design challenges associated with the different temperature sensors that we have just discussed, we have brought together a signal chain starting point that is the lowest powered, fully integrated sensor conditioning and acquisition solution. At the core of the solution, we are highlighting the AD4130, one of our upcoming products that we are sampling now but releasing in a month's time. The benefits of this solution is that it's 24 bits optimized for input signals from DC to 1 kilohertz. Certainly very rich in feature set, which we will discuss in a short while, and the digital features on board offer longevity and enhanced power saving in the end application. For temperature sensors, the AD4130 is actually a complete measurement solution where it has all the integrated features that can be easily exposed to bring value to the end application. If additional signal conditioning is required, such as higher input impedance sensing or special filtering of the front end, then we've highlighted the ADA4505 as a good device to consider. Of course, there are others that can easily be used and will add value. And for this, I'd suggest using our LT Spice to review the actual devices and models, or even go to our Precision Studio online tools, as they really add value. For the product spotlight, let's take a quick look at the 4130. The AD4130 has been designed specifically for low-power, portable, high-density applications. The active current consumption of this device is truly impeccable, 32 microamps in continuous conversion mode. Taking a look at the block diagram of this device on the right-hand side, you will see that it is truly rich in features. Not only does it take care of the sensor biasing and excitation, which is important for some of the sensors that we just discussed, it really has various options available, from selectable excitation current to onboard precision reference voltages that are also selectable. It has power optimization features built in. An example of this is the sync triggered duty cycling operation. Here, the average current consumption can be brought down to as little as 5 microamps, which is really, really impressive. But we've gone even further in terms of integration functionality with a FIFO and smart sequencer on board. This device is really all about integration of all the blocks and features that matter most to achieve the high performance required and enable our customers to really differentiate within their own application and solutions. For this, focus on the FIFO memory, the interrupt capability. These offer reduced burden on the microcontroller and is really useful in battery operated or power sensitive solutions. We also have multiple diagnostics, including CRC reads and write operation, measurement and calibration checks. Certainly differentiation in this space. Another measurement modality within field instruments is pressure sensing of liquids and gases. With this type of end application, accuracy and stability of the measurement is really important and a key challenge. The location of this end solution is usually space constrained, so size is definitely another key consideration. Being able to extract key information from low-level signals is also a key requirement. We will now focus on a signal chain starting point solution that is a discrete, low-power signal conditioner for pressure sensors. Pressure sensors are usually bridge-type sensors, and the same principles that we will discuss here also apply to load cells and strain gauge sensors. Key value proposition and benefits of this signal chain solution is the high channel density, the small footprint, and the ability to control the power of the full solution through GPIO pins from your micro. The signal chain solution has the AD4696 at the core, and this is the hero of the signal chain, where its size, performance, ability to scale power through sample rate, and also the high Z mode makes it a clear differentiator in low power applications. The additional components that we've highlighted here bring even more value to the end application in terms of low power and space saving. The MAX 41400 is the smallest low power in-amp available. It really is tiny, making it applicable for space saving constraints. And it also adds clear value when it comes to bridge sensing applications. We suggest using the MAX 40023 where low leakage or where additional signal biasing is required. For example, high impedance sensors, or to bias the MAX 41400. Let's now put a spotlight on the MAX 41400, which is a low-power, high-precision instrumentation amplifier with gain programmable GPIO pins. This is available in a space-saving 9-bump wafer-level package with a 0.4mm bump pitch. Let's take a quick look at the features of this device. The active current consumption of 65 microamps is truly impressive. Fits in our low-power space as it has an operating voltage of 1.7 volts to 3.6 volts. The Auto Zero feature eliminates 1/F noise and ensures zero input offset drift over temperature and time. Some of the target applications for this are low power sensor interface, such as pressure, weight, and force, also works really well with temperature type sensors, as well as other applications in the medical space. If we put a further spotlight on this device and focus in on the internal resistors that offer that gain selectability of the device, having these resistors internally ensure that there's stable performance over temperature. This simplifies the calibration scheme over temperature. It also saves on system cost, as well as saving on space and improved layout. For our second application focus area, we will look at condition monitoring through the low power lens. In condition-based monitoring, one of the key focus areas is predictive maintenance. And for this, some example measurement modalities include vibration and temperature. Key requirements in this space, especially when we look at low power sensing, is size and accuracy. And because many of these solutions are wireless, long operating time is certainly important. If we look at the types of sensors, the configurability of the end solution is also important in these end applications. Other challenges and requirements around these low power condition-based monitoring applications is the ability to deploy faster and extract more value with access to higher quality data. These solutions are important on how maintenance is performed and how the machines really operate. I suppose reducing downtime, improving efficiencies, and delivering new capabilities are key requirements also. Focusing in on vibration for low power condition-based monitoring applications. Having sufficient bandwidth is necessary to capture information across a wide frequency range. This will help to improve accuracy and confidence of the information being gathered. Improved accuracy is also important, and a wide dynamic range of the solution is certainly comes into its own. Being able to synchronize multiple measurements, knowing at the right point in time, is also important here. If we look again through the low power lens, we have brought together a low power signal chain starting point that offers low noise, low drift, can be applicable to wireless vibration sensing, and has power management optimization for maximum battery lifetime. Here you will see we have brought into the conversation our low power MEMS accelerometer, the ADXL 356. This offers excellent performance in this space and enables quick and easy extraction of information and insights. Low power density, DC performance, and power are key offerings from this accelerometer. For this signal chain solution, we have also brought together some of our best low power signal chain components that really add value in this space, from ensuring that the full solution can easily be power scaled to having low power amps between the ADC and sensor to ensure easy interface and additional filtering where needed. Key for this signal chain is the ability to synchronize the measurements and also have the ability to scale further. The 84000 family of products are an excellent choice here, from their easy drive feature that reduces the burden when interfacing to it. We've also called out our low power BLE enabled MCU, the MAX 36655, as a good solution in this space. I also want to put a spotlight on the ADR 3625, which is our upcoming low power, high accuracy, stable and reliable voltage reference. The ADR 3625 is our precise micropower high current output voltage reference. This is our latest in terms of low power reference from ADI and is due to release in the next few weeks. It's an excellent choice where low power is key. If you look here, the quiescent current is only 65 microns. But not just that, its DC specification and drift numbers are really impressive for such a low power device. Another key advantage to this low power reference is that it can be used as a direct replacement for standard LDOs where space saving is required. It has the combined function of a reference and an LDO. It has high reliability and lifetime accuracy, and unlike LDOs, the quiescent current stays the same when the load increases. It also has low thermal hysteresis, making it ideal for low power applications. So the third and final application focus area is portable medical devices. Let's take a look at these. The past few years have further emphasized the need for medical devices that can monitor the health of patients in the clinic or else remotely to aid in the prevention of disease. There's an increased adoption for accurate real-time monitoring, and there's a need around increased mobility and portability of these end solutions, where the requirements are to gather faster, quicker insights, ensure early detection is achieved. These portable devices are getting smaller. Having long time between charges is ultimately important. Being able to extract small signals is really important in these spaces. And configurability is certainly a key requirement also. Some example measurement modalities in this space are biosignal types measurements such as ECG, EEG, EMG. Temperature and pressure also play an important role. But let's focus on ECG, EEG, EMG for this application. Here we can see the different types of sensors and where they fit in terms of frequency band of interest. And you can also see the different voltage level outputs from these sensors. I won't spend too much time on the specifics of these sensors, but take a look at our Engineer's Own blog spotlight from David Plourde, who goes into a lot more detail, certainly worth a read. Focusing on these sensors, they typically have large offsets associated with them. This can be a challenge as it limits the gain that can be implemented in the signal chain. This in turn has an effect on the overall dynamic range measurable, and this can be even more pronounced when we think about lower supply voltages when it comes to low power battery applications. Dry electrodes are high impedance sensors and certainly offer a challenge when it comes to designing the signal conditioning for these types of sensors. And also, I suppose there's always an undesired presence of interferers that certainly offer a challenge. These include slow-moving baseline wander of a signal, a 1/F noise, and also motion artifacts that can easily be picked up with these sensors. We again have an example signal chain solution that brings together the technology components to help address the challenges associated with these sensor types. The value proposition of the signal chain is that it offers direct connection to high impedance sensors. It can be used to easily remove large offsets using AC coupling, and also offers the ability to connect multiple sensors with a small form factor. The signal chain solution is a great starting point. It's ideal due to its low quiescent current. It offers size, space saving, making it ideal for applications where higher electrode measurements are required. We've the AD8235 in the signal chain to AC couple the signal, thus removing the DC offset so that gain can be implied at the next stage. The rail-to-rail operation of the 8235 is certainly important here as well, because it offers more dynamic range when operating in low voltage applications. And the role of the ADA 4505 here is to help with additional amplification, filtering, biasing of the in-amp also. This technique, AC coupling of the AFE, is not only applicable in this application, but it also applies where signals presented to the signal chain in the form of small differential signals in series with much larger DC offsets. Examples in the industrial space would be EM flow, where the sensor, the output of the sensor certainly has that large offset, and AC coupling technique can be applied to those types of sensors also. You will see here that I've also highlighted throughout the presentation that there are different tools that we have that can be used to further optimize or tweak the design for your end application. Precision Studio online tool, we have Diamond Plot tool, as well as the Filter Wizards. And these offer great value in terms of being able to tweak and tune for your specific requirements and ensure the best optimization and operation is achieved. We also have models for these devices available in LT Spice. We have many of our in-amps and op-amps supported, and we also have a range of ADCs and DACs and switches within these supported also. And we're continuously expanding and adding. The AD4696, which you see here, will also be added soon. Just to talk about the AD4696 in this application, it really adds clear benefit and differentiation in the space. And if we put a spotlight on this product, I'll go through some of the key benefits that apply here and also fit into many more applications. The AD4696 is a game changer in many applications, but especially when we talk to low power applications where space is constrained. The Easy Drive or High Z analog inputs and reference inputs enable high density measurement solutions, making it easier to choose from a broad range of analog front-end solutions. Thus, it offers more flexibility in decisions and trade-offs that need to be made. The Easy Drive feature set also leads to a smaller form factor design, as fewer companion products are needed per channel, thus improving the size and also the power consumption of the end solution. Other key things to note on this device when it comes to power saving is the scalable sample rate, the advanced sequencer that offers flexibility and enables the end solution to be customized and adapted based on the measurement requirements. Autonomous operation with auto cycle mode and threshold detect reduces digital overhead, thus further even improving power saving. So this device is certainly one to keep an eye on, and there's a family of devices available in this space. In addition to the signal chain solutions that we have just discussed, I want to just highlight what we in the signal chain platform team are doing to help accelerate the design journey through the available signal chain collateral. We have a number of online tools that are available within our Precision Studio, and I called some of these out during this webinar. These cover a breadth of different precision technologies on offer from ADI. Each offers key differentiation in the understanding, design, and implementation for your end application. We have a lot of collateral available and much more in development. Here I've highlighted some of the key application notes, quick circuit notes, which are know-how with integrated knowledge and really delve into the signal chain solutions and key building blocks within those signal chain solutions. So make sure you check those out. We have blogs and articles that are all focused on precision low power and really enable key understanding around our products and solutions. We have information on our precision low power landing page on analog.com, but also have a specific support community based in Engineer Zone that is there to help and solve with any questions you may have. So feel free to check this out and come to us if you have any questions. We're continuously developing and implementing collateral for this space. In addition to this, we have LT-SPICE models that can be used to simulate and ensure key performance can be achieved right across the signal chain solutions. We have evaluation hardware, evaluation code that can be easily obtained from our landing pages and are certainly a great starting point for your end application. So today I've spoken about our precision low power signal chains, but we have a number of other signal chain platforms that offer different capabilities and solve different design challenges for a broad number of end applications. Check these out and the associated details on analog.com/precision. And finally, I just want to put a spotlight on where you can find more details on our precision low power signal chains. Check us out on analog.com/precision low power or visit our Engineer Zone community using the link highlighted. You'll also find any key information around our precision technology signal chain platforms on analog.com/precision. And as always, for further information, please make sure to check us out on mouser.com/analog devices.
Thanks, Anya.
Thank you.
We do have a few questions coming, so let's move on to the Q&A. If anybody else, of course, in the meantime, would like to ask anything at all, please do use the Q&A button. But let's start going back to the ADCs, Anya. I think one of the ADCs had a sample rate of up to 1 megahertz. So for low power signal chains, and I guess some of these fairly slow moving parameters that are being measured, why would you use such a device is one of the questions.
That's a really good question, and it's one that I get asked actually quite a bit. So I suppose one of the key things around the ADCs that we've chosen in our signal chains, some of them are SARs or successive approximation ADCs. And really, I suppose these devices can run really quickly, but the beauty of these is that you can actually scale the power by scaling the throughput. So if we run these devices slower, then we can actually optimize the power that they consume. But I suppose if we look at it then through, say, an application where you want to run your application really slow and gather information every now and again, but sometimes you might want to wake up and take information quite quickly. So the beauty of the SAR then is that you can actually tune your sample rate based on what it is you want to do. So that's where I suppose the SAR based solutions that we've chosen here really bring into their own in the low power space, but also add value if you want to run faster or capture more information and do some level of oversampling.
So you get its flexibility, I guess, isn't it?
That's it, exactly. Yeah. What you can go back to some of those key points that we were talking about around the scalability, the configurability. So solutions that we have here can really be tuned based, and they are a starting point, but it's the ability to take them and tune them and bring more value is where these solutions together add value.
Yeah. Okay, thanks. Next up was about choosing the conditioning before the ADC, so that when we're looking at the amplification and the filtering, what needs to be considered when choosing the conditioning before the ADC.
Okay, so I suppose when we look at the conditioning before the ADC, it really depends on the sensor that you're looking to measure, the bandwidth that you want to measure in. So it's not always easy to say you need to use this for this broad set of sensors, because every sensor is slightly different. But what we have done is, I suppose, brought together solutions that can be configured and tuned. But the beauty of the heroes in the signal chain, and I call the ADCs in our signal chain heroes, because they're I suppose the brains of the full solution, or part of the brain anyway of the full solution. And I suppose what ADI has done over the last while is really brought out some breakthrough technology. And if we look at the SAR ADCs in particular, the high Z mode, or the easy drive mode that I highlighted on, say, the 4696 or the 4001, they really add value, because I suppose what they're doing is easing the choice, or making it easier, I suppose, to choose the in-amps and the op-amps that go with them, so that you can easily optimize and tune for your design. But I suppose if we look at that and look at the value that it brings, it's not as stringent anymore to try and figure out what the best amplifier is. There's a huge breadth now that will work. And if we look at the sample rates and slowing down the throughput on those ADCs, this makes it even easier again, because in some cases you can just connect in do a small level of conditioning and bring it into the ADC. If I just talk about an example application, maybe say in optical comms, where you might have a photodiode that you want to take and condition and bring into your measurement. You have to do that current to voltage translation, and then try and figure out how you get that signal to the ADC. But the 4696 as an example, with the high Z mode and the easy drive features on board, you don't even need to think about the buffer in between, or the conditioning in between anymore, because you can just take the output of your TIA and connect it straight in. And that's the beauty of the technology that ADI has brought to the market here.
Right, easing the design effort, right?
Yeah.
And that, which speaks to, I guess, design iterations, time to market, and
exactly.
Engineering costs, and so on. You mentioned easy drive, and actually we have a question from Christian asking, what does that really mean? Can we connect sensors with high source impedance, presumably? These are written resistance, but presumably impedance, directly to the input? And what max source resistances are possible typically?
That's a good question. So the easy drive does make it easier to connect, sensors between, straight into the ADC, but in some cases you might need a buffer. I think the input impedance wouldn't be very, very high. I don't know the number offhand, to be honest, but I can follow up afterwards. But we'd usually recommend, a buffer to really take those high impedance sensors. And we've some examples that we called out there earlier, but we have a tool, it's called our ADC driver tool. The 4696, I believe, is in there. We have all of our in-amps, our ADC drivers called out there, so you can quickly and easily see the performance that you can achieve by hooking up or selecting different input stages to the ADC. So that's definitely one to have a look at as well and try out. But I'll follow up on the input impedance.
I should say as well, we will be providing written answers for all the questions that we've got, and everybody who's joining the webinar will receive those. So look out for that. We've also got Costas asking about CMRR for the ENA. How can we predict the CMRR region with precision?
That's a good question as well. So I suppose, it really depends on the connectivity. I think our LT-Spice might help with some of that, but I'll follow up afterwards with a good answer on that one, if that's okay.
Yeah. Okay. Yeah. Absolutely. Yeah. These often these questions can be need a little bit of thought before they're answered, right? But there's a couple more. Because I think we've mentioned simulation. What simulation SPICE models are available for the components that you showed? Because obviously there's LT SPICE and so on. That's
we have,
well known.
Okay. Yeah, so we have a lot of our devices available in the LT SPICE library. Many of our in-amps and off-amps are there. And if they're not, we have a SPICE model available on all the product pages that can easily be pulled in. But I suppose a key thing that I called out earlier on actually was the fact that we're bringing in, or we're making available models of our ADCs. So it's easy to see the sample rates for the SARS, the sample rate and so on, and the interaction on that front end. So we have a number of them in LT SPICE. The 4001 is definitely in there. We've a test bench that allows you to get up and running and understanding the configuration and optimization of that device. But we are building out solutions for many of our other, I suppose, SAR ADCs, and there's a lot of DACs and so on. But the 469 will be in there shortly as well. But the one thing I suppose that we're looking at doing, and we've got a couple of examples where we're actually building out, so the signal chains that I would have showed you as a starting point in the different applications, we're actually building out LT SPICE signal chain models so that you can actually see the performance. So we're not just telling you that these go together, we're showing you how they go together and how you can optimize further. So keep an eye out on our landing page and you'll see those coming through.
So it means the user can plug in a complete example signal chain rather than building it from individual devices then? Yeah. Excellent. On the subject of tools, Piero's asking, is a tool being planned to calculate the power requirements of a conditioning plus sampling circuit? So I guess the complete signal chain, unless one exists already, of course, he goes on to say.
Yeah, I don't think one exists already. We have, say, for the 4130, so that's our integrated solution. It has a duty cycle mode. There's a lot of configuration and feature set on board there. We're definitely developing a tool that will allow, the understanding of the power and timing that goes with that. In terms of a tool on its own, we don't have one as such, but you raise a good point.
Yeah, good point. Interesting point to see the customers, the user's perspective here, isn't it? The designer's perspective. Also, one other thing you mentioned, and this is the last question I have for now, is you mentioned quick circuit notes.
Okay.
It might be worth just saying, because somebody's asked, what is a quick circuit note and where can they be found?
Okay. So I suppose quick circuit note, we've denoted it's a new piece of collateral that we're developing from the Precision group, and it's all about, I suppose, quick is know-how with integrated knowledge, and it's a circuit note or an FAQ that really zones in on a specific challenge within the signal chain or an application, and it really is a step-by-step guide that has generic formula and goes through kind of how to the building blocks that are needed to go from bottoms up in terms of a design for a particular signal chain solution. So it's something that can be easily rescaled. So we've done some quick circuits for ADC drivers and selecting the right solutions. We also have done a couple around modeling of the sensors and what you need to consider. And with those, we have example LT SPICE models so that you can actually follow along and figure it out hand in hand. So they're available on our Engineers Own site, actually.
Okay. Great. Thanks, Anya. I think perhaps that's one of the things, if we put in the written answers, is pointers to Engineering Zone and other useful resources relating to what we've been discussing today. So With that, we'll wrap it up there. Thank you again, Anya, and thank you everyone actually for joining today. As I said, questions will be answered in writing and be made available to all participants. And if you'd like to watch the webinar again and remind yourself of some of the information that was in there, it will be made available on demand in the next few days. And finally, I would say there is a short survey coming up, so we'd be grateful if you could provide feedback to help improve the overall webinar experience. So with that, I'll say thanks again, everyone, and enjoy the rest of the day.
Thanks, everyone.